Okay, yesterday I gave you some bivariate data, and I remember these are fancy names for this. This is called our explanatory variable. This is the response variable. But what we were talking about is this is an extinct animal, and if I gave you the length of the femur, we were trying to predict the length of the humerus. Okay, so we had 5 points to try to predict this, and we went through yesterday on how we can determine whether a line is a good fit or not. The first thing that we took a look at is we took a look at the graph. Okay, does the graph look like it could be a straight line or not? And also we were looking at, does our graph show us a positive association? In other words, as the femur gets bigger, does the humerus get bigger? Or might there be a negative association? As the femur gets bigger, the humerus will get smaller. Or maybe no association at all. Okay, in which case, no matter what happens with the femur, the humerus is going to stay exactly the same. So we looked at that visually. I think we saw some positive association. We thought that a line might be a decent choice. Anthony, pay attention, man. This is what you're focused on right now. We'll get to all that later. All right, then what else did we have to analyze? We took a look at the correlation. And in this problem, the correlation was 0.99, so we had a very strong positive linear association. We took a look at R squared, which is like 98.5%. 98.5% of the variation is explained by the least squared regression line predicting humerus given femur. We also calculated the standard error. In other words, if we're predicting humerus, we're usually off by about 2 inches, what we came up with. And then finally we looked at the residual plot. And we saw no pattern there, so we're saying, okay, since there's no pattern in the residual plot, that tells us that we could have a linear relationship. So we looked at all 5 of these things, looking at the equation that we got, and a line looks like a very good pick. We're going to add one more thing to this list today, okay? And we're going to try to prove that there is, in fact, a relationship here. Now, wait a minute. What does that mean? I got this slope, 1.20, from this little sample of 5 animals that we're able to dig up. Okay? Is that enough evidence? Is that slope enough evidence that if I got every single animal that there ever was, and I fit a line to it, that I would in fact have a relationship? In other words, if I know the femur gets bigger, the humerus is going to get bigger. Or, because it's such a small sample size, that's not far enough away for 0 for us to know for sure that if I had all of them, that I would in fact have a relationship. So how do we do that? We're just going to analyze the slope. It's called the slope test. And based on these 5 points I got this slope, is that enough evidence that the population slope would in fact be a number, not 0? Because it's the 0 slope that would mean no relationship at all. No matter what happens with the femur, it doesn't affect the humerus length at all. So that's our last check of all the things that we can do to see if a line is a good fit or not. So we got 2 options. We can build a confidence interval around that sample slope, or we'll do a hypothesis test around that sample slope. And that's what we're going to work on today. Okay? All right, first things first. Let's analyze this thing called the sampling distribution of all the possible slopes. Let's go back and remember what a sampling distribution is. I went and got 5 of these guys, and I got a sample slope. Well, that's one of the elements of the sampling distribution. Now you'll get another sample of 5 animals, and I get a slope for that. Another sample of the 5, another slope, another. Every possible sample slope that I could get of size 5. That's the sampling distribution of all the possible slopes. I'll tell you right now that slopes is an unbiased statistic. In other words, if I took the mean of all of these sample slopes, it would be equal to the population slope. And I'll tell you something else. The shape of all of these sample slopes will be normal if a couple of conditions are met. So this is what we're going to be doing in our assumptions. The first thing that we need to know is that our residual plot shows no pattern. So that one thing we looked at over there, that's one of the assumptions that we need to meet. And the other one is that there's no great skewness or outliers in those residuals. So if those 2 conditions are met, then we can safely assume that the sampling distribution of all the possible sample slopes would be normal. So the last thing we have to talk about is how spread out are these guys going to be. Go to the first page of your formula sheets and look at the very last formula on that page. That first page, that has all the formulas on it. The one that has all the formulas on it, the first page. Look at the very last one. There you go. That's the formula that tells us how spread out all those sample slopes are. But I want you to take a very close look at the numerator. What do you see there? Just look at the numerator. What is that?
Isn't that the standard error?
That's the standard error formula. That top is SS resid. You know all the y's from the y hat line squared divided by n minus 2 square root. So the top is standard error. In this little problem we just did, the top is 1.98. Okay, the bottom, what we got to do is we got to take all the x values. So which one of these is the x values? They're in L1, right? We got to take all these, subtract the mean of these, then square them, add them up, and square root that. Go do that. Go find the denominator now. See if we can all get the same number here for the denominator. Okay, so we're trying to find the denominator of that big ugly formula. Anybody get a number yet for that bottom? Just the bottom? What'd you get? What'd you get?
696.
But you think you have to square root that. You got 600 something?
Oh.
Right, look at the formula. Alright, let's do it together if you're lost. Okay, so what that formula says is I've got to take all the numbers in L1 and subtract it from the mean of the L1s. Alright, so I'll see if I can do this right. So L1 minus, and there's a way you can go get the mean. We did this before on your calculator. It's in list. So if you go second stat, over to math, down to mean, that's one way to do it. All those deviations, those are all the deviations. So after I find those deviations, I'm supposed to square them and then add them up. Remember, we have that fancy key that does that for us. Okay, so if I go stat, calculate, do a 1-var stat on L4, that squares them and adds them all up. So, in terms of this formula, the top turns out to be just standard error, 1.98. The bottom turns out to be what's the square root of the 696.8. And I think that's something like 0.0075 or just 7.
0.07.
Inches. So all these sample slopes, if I got them all, the whole sampling distribution, they'd be centered at the real population mean, and they're about this far away from whatever that mean what that mean population slope is. Okay? Okay, let's forge ahead. Let's go do it. We got all the stuff we need now to create a confidence interval around that 1.2. And we've got all the stuff that we need to do a hypothesis test around that 1.2. All right, so we're just working together here now. Copy this stuff right now. Let's work together on the confidence interval. All right, population parameter. What are we on the hunt for? What's the symbol? What are we looking for? What are we looking for? Beta. Yeah. We're trying to figure out the real population slope. So the true slope of the least squared regression line predicting humorous length given field. Yeah, if I had every single one of those skeletons, and I graphed every one of those points, and I fit a line to it, that would be my best fitting line for the population of points. Remember, I just have a sample line, because I only had 5 of these skeletons. Okay, assumptions. Number 1, simple random sample, just like we've always done before. How did I get those 5? You want to talk about that? All right, assumption 2 is the sampling distribution of the sample slopes normal. And I draw this picture. Will all these sample slopes create a normal distribution? Very similar to how we did the sampling distribution of the x-bars, sampling distributions of the p's. This is sampling distribution of all the possible sample slopes. Will this come out to have a normal shape? 2 things we got to check out. First of all, we got to look at the residual plot. So you just copy that guy. What does it look like? Talk about it. No pattern. Residual plot. Check. Second thing we have to check out is to make sure that there are no great skewedness or outliers in the residuals. So what graph do you guys want to do? You have a couple of options that we've done here. Which graph do you want to use on this one to look at the residuals? Boxplot, that's one of them. You guys have also used normal probability plots here, right? Looking for the straight lines, whichever one you want. So hopefully you have your residuals still there. So go do a box plot or a normal probability plot on those residuals for this problem. So you don't have the data in there. Go put your residuals real quick. Get a shape that looks something like this. Pretty skewed. No outliers. That is pretty skewed. So, skewed right. It's cause for concern. It's a pretty major skew right there. So, remember, a little bit of skewedness, that's not a problem at all. If you have outliers or major skewedness, that would be cause for concern for that particular assumption. And then finally, the third assumption, we are using a t-distribution here. And that's because sigma, the population standard deviation, is unknown. Okay, here's our formula to calculate the confidence interval. We're going to start with our sample slope. We're going to go a certain number of standard deviations and then multiply it by the formula for the standard error of the slopes. Okay, so how do we write that up? Start with our sample slope, plus or minus t crit, and then just copy that big giant formula right off your green sheets. Okay, numerator, y minus y hat squared over n minus 2. The denominator, summation. The denominator is the summation of x minus x bar squared. Bivariate data, so our degrees of freedom is n minus 2. All right, calculations. Our sample slope was 1.2. Plus or minus, go, you haven't used your t-charts in a while, go to your t-charts. Let's do a 95% confidence interval. How many standard deviations do we need to go both ways to capture 95% of the sample slopes? What's our degrees of freedom for this? It'll be what? 3. It's 3. 5 minus 2 is 3. So 5 points here. Anybody get a T number? 3 point something? 3.182, is that correct? Okay, now on this side, okay, just kind of put some of our stuff here. So we know that this was 1.98, so put 1.98 on the top. And on the bottom, let's do what we did over there. Square root of 696.8 over, that's it. One way you can kind of show what we've got here. All right, throw that guy into your calculator. What is our 1.2 plus or minus what is our margin of error? So you can get that thing into your calculator. Oh yeah, 0.239, is that right? Is that right for the margin of error, 0.239? Any confirmation out there?
Yes. Yeah.
0.239, is that for sure?
Yes.
For sure? All right, so let's remember the big picture of what we're doing here. We're trying to see if the population slope is in fact not 0. Because if we have a population slope, that means there's a relationship here between these two variables. Is 0 going to be in that interval? No, not even close. So what that tells us is we only got 5 skeletons of the millions and millions and millions that exist. But just based on those 5 skeletons, we're sure that if we got all of them together, we would in fact have a slope, therefore we would in fact have a relationship. All right, we got our same 2-sentence conclusion. Before taking our sample, 95% of all the sample slopes would create an interval that captures the true population slope of predicting humerus length given femur. Our 95% confidence interval is. Okay? All right, let's move. Yeah. That's what we're going to do right now. Set up here for us. Let's go. All right, we'll do what's different and what's the same. How about population parameter? Anything different from what we did over there? Nothing different. Okay, we just write that again. All right, let's talk about the null and alternate here. Some of you, I don't know if in this class or not, but some of you got the null and alternate backwards on the chi-squared. So what are we going to assume to be true? What do you think? There's 2 ways we can say this, okay? Yeah. It's 0. What's 0? What is? What symbol? Beta. Yeah, well, we'll assume there's no slope. Now, another way to say this is we're assuming that there is no relationship. It's kind of like chi-squared, right? Assuming that they're independent of each other. They don't have a relationship at all. Now, alternate, you've got options here. Maybe you're trying to prove that it has a positive relationship. Maybe you're trying to prove that it has a negative relationship. Maybe you're just trying to prove that, I don't know if it's positive or negative, I just know it's not 0. So another way to say this is we're trying to show that there is a relationship, a positive relationship between humerus and femur. Level of significance, it's one-sided. To match that, I guess that'd be 2.5%. We're going to match this guy. Assumptions, anything change here? Same exact assumptions. We want to know if we have that normal sampling distribution or not. We're actually going to draw the picture here, right? We draw the picture in a hypothesis test. Okay, our test statistic. Trying to find the t-score here. We're going to take our sample slope, and actually sample slope minus 0, divided by, put that big giant formula in there. We want to know how many standard deviations 1.2 is away from 0. Is that a big deal, getting a 1.2? Alright, so this thing is square root, summation, y minus y hat squared over n minus 2, square root, x minus x bar squared. Degrees of freedom, still n minus 2. Alright, let's go find that t-score. So it's 1.2 minus 0, and then we got that same game here. So I guess 1.98 divided by the square root of 696.8. Throw that into your calculator, see what we get. How many standard deviations is 1.2 away from 0? Big number?
15.99.
What'd you get?
15.99.
Yeah, it's like 16, right? That is a very big number, right? Okay, let's draw our picture. These are all the possible sample slopes. We assume that the population slope is 0. We got 1.2. Turns out that's 16 standard deviations. Check out your charts, 3 degrees of freedom. My guess is that's pretty unlikely that we would get a slope of 1.2 if the true population slope was 0. Check your check your T charts at 3 degrees of freedom. Is it off the charts? Is it off the charts? So I got some people still don't know their less than and greater than symbols, which is scary. There's less than 0.0005. Translation, it's impossible. It's impossible to get a slope like this if the real population slope would have been 0. Not happening. Beyond a reasonable doubt. Same 3-sentence conclusion we've done before, assuming that the true slope of humerus given femur is 0, or assuming that there's no linear relationship between predicting humerus given femur. Just means the same thing. There is literally no chance, less than 0.0005, of getting a sample slope of 1.2 or more. Because our p-value is lower than our alpha level, we'll reject. Therefore, we do have statistically significant evidence that we have a positive relationship between those two variables. Okay? So, if I'm trying to prove that a line is the best fit, I got these 5 to do, and now I've got a 6th thing to do. Trying to project onto the population of all points to make sure we have a relationship or not. Okay, well, in May, I hope they give us a question like this, but it'd be nice if they gave us some Minitab output. Let me show you why. Go to page 790. And generally, the problems that I've seen on the AP test, they have given a Minitab output for this problem, this type of problem. You see a lot of writing in your books. Founding fathers have put notes in there. That's okay. I told them to go ahead and do that. But let's analyze this. Yesterday, we talked about where you find the equation of a line in Minitab output. We also talked about that bottom left number. That's the standard error, right? Okay, but now let's take a closer look. All of those numbers on the line with the y-intercept, forget about them. We don't care about those. But the numbers on the line with the slope, because aren't we doing slope analysis here? Okay, the next number, the standard deviation of the slopes. What is that? It's our standard error of the slopes. I'll give it to you right there in the Minitab output. The next one over from that, the t-score. What do you think that is? It's old 16 right here. Did that math for you. And the next one next to that, the p-value. That's this guy right here. Okay, so with the mini tab output, they give you all that information. Now, does any stuff up here change?
Nope.
No, we just did all the nice calculations for you. Yeah.
What is the T and the P for the constant?
They don't. If you were doing some analysis on the y-intercept, we're not doing any analysis on the y-intercept. We just want to focus on the slope. So if you're doing some hypothesis test, seeing if the y-intercept is 0 or not, those are the numbers you get. Okay. So tomorrow in the quiz, we'll do a hypothesis test or a confidence interval and the sample slope, and that'll be what your quiz will be about tomorrow. No multiple choice, nothing like that. We're just going to go. Okay. Questions, comments?